Logistic equations, a widely used model for population because they can account for limitations to growth like food or the competition between species, water sources, all sorts of things like that, is what's called a logistic differential equation. And it has this form where k being bigger than 0 is the growth constant, and a also being bigger than 0 is called the carrying capacity. And what the carrying capacity does is it slows down this rate of growth at high values. And so what y of t often looks like is a function that starts at some initial value of y, and it increases kind of like an exponential, at least to start, and then it starts to slow down and flatten out, and basically has some maximum value, which is your a value, and so it starts to slow down. And so you get population growth that goes exponential, lots and lots and lots of bunny rabbits. They eat everything. They can't have offspring as quickly, or the predators start eating them because there's lots of them, and their population will slow and stabilize. So there's actually 3 families of solutions. So if we expanded this and thought about this being 0, here's your y-axis. So where you have an a value here, if you started with an initial condition anywhere above it, you will eventually level out to it. If you start with an initial condition inside this zone, you will move up to it. And if you end up choosing an initial condition that's below 0, basically this just takes off and goes to negative infinity. So there's this like stable line at 0. This kind of function will decrease. This kind of function will increase. And this one just decreases to negative infinity, as I said. So the stable solutions are ones that come to an equilibrium. They're called equilibrium solutions, and that's basically these two. As they go towards infinity, they start to stabilize. So the general non-equilibrium solution looks like this. And again, the non-equilibrium solutions are where it decreases or where it increases. Only A is really an equilibrium solution because it never changes. So we start off with a differential equation like this, and we get a general solution y equals A, all divided by 1 minus e negative t over c. So let's take a look how to use this. Here's an example, in which case we're solving y dot equals 0.3y times 4 minus y with the initial condition y of 0 is 1. So y dot is 1.2y. If I just multiply this through and get it into the same form as I have above, so just factoring out a 4, I get 1.2y. So this now tells me what my k value is, which is 1.2, and this part tells me that my a value is 4, which can lead to me getting a solution, and that says y equals 1, and we can now substitute in our initial condition. So 1 is equal to 4 over 1 minus e to the negative 1.2. just continue this over this way. We get 1 equals 1 minus 1 over c over 4, or 3 equals negative 1 over c. So the c value is equal to negative 1 to the negative 1.2t when I substitute it back in. So there is an example with no context. It's simply some slope fields, some logarithmic differential equation. But let's take a look and see how this can be applied to populations. Okay, so we have a deer population growing logistically with a growth factor of 0.1 years to the negative 1 in a forest with a carrying capacity of 3,000 deer. So we're going to find the population function, p of t. That's what we're looking for in this case. And we know that p of 0 is 200, that at the initial condition there's 200. And we also know that the k value is 0.1, and we know that the a value is 3,000. And we can put in our initial population of 200, 1 over c, and we're going to solve this almost the exact same way that we did in the last question. You'll end up with c is equal to negative 1 over 14, and therefore your population must be 3,000 over 1 plus, this will turn into 14e to the negative 0.1t. And again, create a growth chart that starts off with a population of 200, it goes up exponentially, and then starts to, where this a value is 3,000, and again, this beginning value is. And then you can ask a question like, when are there 2,000 deer? And now that we have a formula, we can just put in that the population is for t. So I'll leave that to you. This isn't too difficult to solve for t, but you get about 33 and a bit years. And so we can start to estimate where different populations are at once we have this population equation.